Right. Welcome to the second lecture in source coding in the series on source coding. Again, this is an informal set of lectures on data compression. In this lecture, I'll cover fixed length compression, and in particular, you'll see a proof of the source coding theorem and what typical sets are, and how they're very powerful tools in proving source coding theorems. Okay, let's revisit the fixed length compression problem. The problem is as follows. We are given a file which consists of n symbols. Let's call this file xn. Our goal is to compress this to a sequence or a compressed file ck. So ck is going to be a binary file with k bits. So k is the size of the compressed file. And you have a separate algorithm which we call the decompressor, which takes the compressed file as input and outputs xn or some faithful representation of xn. Right? So we assume that the input xn has n symbols, each of which comes from some set script x, which we call the alphabet, the source alphabet. Right. So xn is a sequence in script x to the n. At least for the purpose of this video, we'll assume that the sequence is IID. So each component of xn is independent and identically distributed according to some known distribution px. So px is a distribution on script x, and for now we'll assume that px is known, it's given to us. So this assumption of the sequence being IID is of course quite unrealistic in practice. Typical files are not independent, so symbols in a typical file are not typically independent and identically distributed, but this is kind of the simplest model that we can work with, and it turns out that the whole theory that we develop with this assumption also generally holds for cases even when we don't have this assumption. In particular, many, for example, text files can be modeled as sequences with a small amount of memory, and even such models can be handled in practice with suitable massaging of various techniques. So this is the simplest non-trivial problem that we can handle, and we'll see how to solve this completely. Right. So such a source where or a file xn, which is independent and identically distributed, is sometimes called a memoryless source. Right. So it's a memoryless source. So our goal is to come up with these algorithms, compressor and decompressor. So the compressor is a function f from which takes an n-length sequence as input and gives a binary sequence as output. Right. And the decompressor is a sequence which takes a binary sequence as input, k-length binary sequence as the input, and gives an n-length sequence from the alphabet x as the output. Now, if there's no other additional restriction on n and k, then it's easy just to use the identity map, and you can reconstruct. So that becomes trivial. So what we want is to get a handle on the file size. Right? So the rate of any compression scheme R is defined as the ratio k over n, and we want the rate of the compression scheme to be as small as possible. Now, just having bounds on the rate is not sufficient. We also want to know when the output is equal to the input, that is when the decompressed file is equal to the compressed file. Now clearly, if k is strictly less than n, then there should be at least some sequences xn such that xn hat is not equal to xn. This follows from the pigeonhole principle. But in some sense we want to minimize the error. So the probability of error is defined as the probability that the reconstructed file xn hat is not equal to xn. And our goal is to have a small probability of error, right? So the probability, so our goal is to somehow design an algorithm which simultaneously minimizes the rate as well as the probability of error, right? So that's the goal of fixed length compression. Note that k must remain fixed in the sense that the designer, the person who has to design the compression and the decompression algorithm is given px, and he has to choose k. So k can be a function of, and in general will be a function of, the distribution px, but k should not depend on the realization of xn. So someone gives you a px, your goal is to design k, f and g such that the rate is as small as possible and the probability of error is as small as possible, right? So one thing to note is that is perhaps to keep in mind the following trivial solutions. The first solution, if you want a probability of error if equal to 0, then you can always have the identity map in the sense that you represent each alphabet, each sequence in its binary form exactly. So how many bits would that require? That would require n times log size of x, many bits. So this is trivially achievable with 0 error. At the same time, if you wanted an ultimate reduction, so this is the best probability of error that we can possibly achieve, but as long as k is strictly less than n times log size of x, so the probability of error will be greater than 0. So if we want the probability of error, so the trivial solution to have 0 probability of error is to choose k to be n times log size of x. But on the other hand, if we can also achieve, if we don't have any constraints on the probability of error, then r can be made as small as possible. In particular, you could choose r equal to 0. So irrespective of what xn is, ck is always the same, right? So that gives you a rate of equal to 0. In particular, you don't need even a single bit to represent ck. The decompressor always outputs the same sequence irrespective of what happens. So you don't even need compression in some sense. So a rate of r equal to 0 is achievable, but for that particular scheme, which is a bad scheme, you have a probability of error of equal to 1. Well, not exactly 1, but 1 minus the probability of observing that particular sequence which the decompressor outputs, right? So those are these two are sort of very trivial schemes. These are bad schemes, of course, and our goal is to come up with something in between, right? So we want small r, small probability of error. In particular, we'll be interested in the regime where n is very large. So we'll only deal with asymptotics because it turns out that that's the kind of the simplest problem formulation that we can handle. So we'll be looking at n tending to infinity, and our goal is to design f and g. So the goal is to design these algorithms f and g such that you minimize r, but at the same time you have the following constraint, that the probability, or in other words, what we want to minimize is r asymptotically, under the constraint that the probability of error is vanishing in n. So as n tends to infinity, the probability of error should tend to 0, but at the same time we want r to be, the asymptotic value of r to be as small as possible, right? So that's going to be the goal of this particular lecture. Okay, so now let's see, I'll show that any fixed length compression scheme can be described in a very nice form. So let's revisit the basic problem formulation. We have a map F, which is, so the encoder or the compressor is going to be a map from xn to 0, 1 to the k, and G is a map from the decompressor, or sometimes called the decoder, is a map from 0, 1 to the k to xn, right? So it takes a compressed file as input and outputs an estimate of the raw file. So note that G is a deterministic map, and if you're designing G intelligently, then G should be a one-to-one map. Right? If you have a many-to-one map, then you're going to get confused between two. Then it's wasteful because you are using multiple compressed files to represent the same raw file. So each raw file should be mapped to a different compressed file, right, by G. So G should map each compressed file to a unique raw file, because otherwise, if you think about it, you're just wasting space. You want to, after all, optimize over R, right? So G should be a one-to-one map, and in some sense, the entire compression algorithm really depends on the performance of the compression algorithm, depends on the range of G, right? So once you know the range of G, at least with respect to the probability of error and the rate, the performance doesn't vary. So what do I mean by this? So let's look at G. So you have a set of all binary sequences of length k, and G takes these binary sequences to sequences in xn, right? And hopefully this is going to be a one-to-one map, because otherwise you can always get a better one-to-one map than the compression algorithm, right? Okay, so G is a map from 0, 1 to the k to x to the n. There are some sequences, since the size of xn is bigger than 2 to the k, there are going to be some sequences which are not going to be the output of G. So the range of G is going to be a strict subset of script x to the n, right? Now you should notice that if I interchange this map, so in particular, if I permute these, so suppose that I have a sequence 0, 0, 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 0, 1, 1. Let's take 4 sequences as example. So these are 4 compressed files, and suppose that this is mapped to by G to x1n, this is mapped to x2n, x3n, and x4n. Now even if I interchange the maps, so if I now define a new decompressor, or if instead I had a different compression scheme where the decompressor mapped 0, 0, 0, 0 to x2n, 0, 0, 0, 1 to x1n, and maybe 0, 0, 1, 0, 0 to x4n, and 0, 1, 1, 1 to x3n, the rate of the scheme would not change, right? So the rate remains the same. So that is point number 1. And the point number 2 is that now once you have this sequence mapped, so let's take a simple example to illustrate this better. So assume that the input file consists of 4 sequences x1n, or say 5 sequences n, 3n, x4n, and x5n. Okay, so assume that there are 5 sequences, 5 symbols, 5 possible source files, right? And I want to represent this using 2 bits, 0, 0, 1, 1, 0, and 1, 1, right? And so this is, you have f, which maps the the input files to the compressed files, and then you have a mapped g, x3n, n, and x5, right? So now let's assume that I map suppose that this is the mapping, right? Suppose, so this describes one compressor. So if the input is x3n, the compression algorithm is going to output 1, 0. If the input file is x4n, then the compression algorithm is going to output 1, 1, and so on. And what does the decompressor do? If it sees, if it gets 0, 0 as input, it will output x1n. If it gets 0, 1 as output, as input, it will output x2n, and so on. So basically both f and g are going to store a table of possible input sequences and possible binary and possible code words, right? But also it's important to note that what does the compressor do when it sees x phi n as input, right? So you could map x phi n to any code word you want, but the decoder remains the same. The decompressor does the same thing. So even if the encoder, so if the encoder sees x4n, it's going to output 1, 1. If the encoder sees x5n, it's going to output 1, 1. By encoder I mean compressor. But the decoder, if it sees as input x1, 1, if it sees as input 1, 1, then it's going to output x4n and never x5n. So this compression algorithm is going to make an error if the input file is x5n, right? Because if the input is x5n, then the decompressor is never going to output x5n, and therefore that is going to be an error. If the input file is x1, x2, x3, or x4, it's going to be faithfully represented at the output. The decompressor is going to give back x4n even after compression. Okay, so the first thing to note is that I can map x5n to any sequence I want. It doesn't matter, right? So in terms of the rate and the probability of error, the probability of error remains the same irrespective of whether x5n is mapped to 1, 1, or to 1, 0, or to 0, 1, or to 0, 0, because x5n is not going to be reconstructed at the output at all, right? So this encoding map is invariant to, or the probability of error and the rate are both invariant to how I map, invariant to what I map x5n to. I could map this to any other sequence I want, but as long as the maps to x1, x2, x3, x4 remain the same, right? Okay, so that's point number 1. The second point, right, so that's point number 1. Right. So the second point is that suppose that 0, 0, suppose that G maps 0, 0 to x1, 0, 1 to x2, 0, 1 to x3, and 1, 1 to x4. So suppose that someone gives you the decoder, right? Then there is only, then in some sense the encoder, a sensible encoder should always do the following. It should always map x1 to 0 0, x2 to 0 0 1, x3 to 1 0, and x4 to 1 1. And it can map x5 to anything. It could map x5 to 1 0, for example. Because otherwise, for example, if I mapped 0 0, if this was the encoder, then it would be bad, because every time x1 and x2, because x1 is mapped by the encoder to 0 1, but the decoder outputs x2, whereas if the encoder maps x2 to 0 0, but the decoder outputs x1, and they would both be in error, right? So if someone tells you what the decoder is, then the encoder has to follow this, right? So in particular, if g of ck equal to 10, then a good encoder should always map xn to ck. So that is one thing. But then if xn, if some x1n, some x5n is not in the range of g, then it doesn't matter what that is mapped to, right? So that is point number one. The second point is, if I have two codes or two compression decompression algorithms which have the same range. So in this example, the range of G is x1, x2, x3, x4, right? If I have another code which has the range being x1, x2, x3, x4, then the performance is essentially identical. So suppose that, so this is another code, right? It has the same range. The encoder must obviously be designed in this fashion, right? Now this has the same rate, it's still 2/5, and it has the same probability of error, because you make an error only if the input file is x5. So in this case, the probability of error is the probability of observing x5, and of x5n, right? So in some sense, permuting these doesn't matter. So how I map these xi's to sequences do not matter, as long as the range is fixed for the same range, and as long as you choose f intelligently enough, right? So what I want to perhaps emphasize is that for a compression algorithm, essentially everything is captured by the range of G. So once you fix what the range of G is going to be, a good compression scheme is automatically fixed. So if I choose the range to be x2, x3, x4, x5, then I can map these four binary sequences to x2, x3, x4, x5 in any manner I want, as long as it's a one-to-one map, right? So G has to be one-to-one, and F has to satisfy this property that if G of ck is xn, then f of xn should be equal to ck, right? So in some sense, the entire compression algorithm can be described by the range of G, right? Any good compression algorithm can be described by this set, which the script X, script S, which is a subset of Xn. So the class of deterministic compression algorithms are going to be fully described by this set S, which I call the set of reconstructible sequences. So this whole set is script X to the N, and this is the set S, which is going to have size 2 to the k, right? So the set of reconstructible sequences has size 2 to the k, and zero 1 to the k, and once you describe S, the compression and decompression algorithm becomes almost completely specified, because a good compression algorithm should be a one-to-one map from 0 1 to the k to S. It can be any one-to-one map, because for every one-to-one map from 0 1 to the k to S, the probability of error remains the same and the rate also remains the same, right? And with this, the compression algorithm also becomes automatically determined. So within S, so this is G, so within S, F is simply G inverse. So when restricted to S, F is equal to G inverse, and in S complement, it doesn't matter how you map elements in S complement to binary sequences. In particular, you could just map all the elements of S complement to a single sequence, maybe the all zero sequence, because ultimately that doesn't affect the probability of error, because sequences in S complement will not be reconstructed anyway, right? So for such compression decompression algorithms, for such fixed length compression algorithms, decompression algorithms, the probability of error is simply the probability that you observe a sequence which is not reconstructible, right? So this is sum overall xn complement. So perhaps one nice way to write this is 1 minus the probability that xn is in S. So it's this 1 minus sum overall xn in S of pxn of x, right? So this is the probability of error. And what about the rate? The rate is simply 1 over n log size of S, right? So it's k over n, and this is equal to 1 over n log size of S, and generally we'll take S to be 2 to the k for some integer k. Okay. So to summarize, any fixed length compression scheme can be completely described by this S. So invariant to invariant to a permutation within G. So G, so right. All right. So now that we have this, the question is, how do you choose the set S? In the previous lecture, we saw that if we want to minimize the probability of error for a given rate, then the way you should choose S is to choose is to take all the sequences which have the highest probability, right? So just this tells us that if you want to minimize the probability of error, then you have to maximize this, or basically you have to choose S to be the sequences with the highest probability. We order the sequences in the order of decreasing probability, choose the top 2 to the k sequences, put those in S, and then select an arbitrary G and select F to be equal to G inverse, right? So that is the best compression scheme, but unfortunately we don't really know how to analyze it perfectly. So again, when I mean that we don't know how to analyze it perfectly, we don't have a good handle on the rate R. So we want to get a closed form expression for R. Okay. So how do we choose S? Now typically, to get a bound on the rate bound on the rate, we'll choose S according to, we'll choose certain specific S, right? So two classical examples are the classes of typical sets. These typical sets are special sets which are determined by the distribution Px, and they will be, and they turn out to be very useful tools both for analyzing source codes as well as channel codes. Okay, so what is a weakly typical set? A weakly typical set is described by two parameters. A quantity epsilon, a small number epsilon, which is typically chosen to be between 0 and 1, and distribution Px on the alphabet script x. It's also determined by the parameter n. Epsilon, n, and Px are three parameters which completely specify a weakly typical set. And this is defined as the set of all those sequences xn whose probability, so Pxn xn, so for an IID sequence, this is product I going from 1 through n of Px of xi, right? And this is between 2 to the minus n times the entropy of x plus epsilon and 2 to the minus n times entropy minus epsilon. Recall that h of x is sum x in x of Px of x log 1 over Px of x. Another very useful representation is to write this as the expectation with respect to the distribution Px of log 1 over Px of x, right? So this is the entropy of x. Now instead we'll use the following set, which is called a strongly typical set. So this is one candidate of S, which helps us get a bound on the rate, the achievable rate for compression. So our goal is to design a good compression algorithm. So basically a compression algorithm for which the probability of error is vanishing in n and the rate is as small as possible. So this turns out to give a good rate, in fact the best possible rate. But there's also another candidate which I call the strongly typical set, which also gives you essentially the same rate asymptotically. So to define the strongly typical set, I need the concept of the type of a sequence. So given any sequence xn, the type is going to be a probability mass function. It's denoted mu xn, and for any a in script x, in the alphabet script x, a mu xn of a basically gives you the fraction of a's in that particular sequence. So for example, if I have a binary sequence 0 1 0 1 0, then there are 2 1s and 3 zeros, so the type is mu xn 0 is 3 over 5 and mu xn of 1 is 2 over 5. Okay, so a nice representation of mu xn of a is using indicator functions. So I define an indicator function 1 1a of x is equal to 1 if a is equal to x and 0 if a is not equal to x, right? And in terms of the indicator functions, mu xn of a is some I going from 1 through n of the indicator a of xi whole divided by n, right? And the reason why this is so useful is when you see what the expectation of mu xn of a is. So if you take xn to be a random sequence, then the expectation of mu xn of a for any symbol a is, again by linearity of expectation, some I going from 1 through n of the expectation of the indicator a of xi divided by n. But what is this equal to? I want you to pause the video and tell me what the expectation of the indicator a of xi is equal to. Right. So the expectation of the indicator is simply equal to the probability that x is equal to a, right? Because indicator is equal to 1 if a is equal to x and 0 otherwise. So this is simply px of a times n divided by n. So the expected type of any IID sequence is equal to px of a, right? So it's equal to the true probability. So the expected value of the type is equal to the true probability mass function. And the strongly typical set essentially captures this property. The strongly typical set, denoted T epsilon strong of n of px, is the set of all those sequences whose type is very close to the true probability. So it's the set of all sequences xn such that the type mu xn of a minus px of a in absolute value is less than or equal to epsilon times px of a, and this happens for all symbols in the alphabet x, right? Okay. And one reason why why I call this the strongly typical set, whereas I call this the weakly typical set, is that you can show that every sequence in the strongly typical set, sorry, yeah. So it's a strongly typical set because the condition is stronger than the weakly typical set. Right? You can show that every sequence in the strongly typical set is also in the weakly typical set for a slightly different parameter epsilon. So T epsilon strong is going to be a subset of T epsilon prime weak for a suitably chosen epsilon prime. All right. So let's see what the properties of these typical sets are and how they're useful in the context of our fixed length compression problem. So the first property is that the strongly typical set is a high probability set, and in particular you can easily show that the probability that xn, a random sequence, is not in the strongly typical set decays exponentially with n. So this is less than or equal to 2 to the minus n alpha times epsilon square for some alpha which depends on px. And this is simply a consequence of Chernov's bound. Essentially, so if you look at the probability that xn is not in T epsilon strong, right? So this is the probability that mu xn of a minus px of a is greater than, so the probability that xn is not typical is the probability that the type is greater than epsilon px. The difference between the type and px is greater than epsilon px of a for some a in x, and using the union bound, this is less than or equal to sum over all a in x of the probability that mu xn of a minus px of a is greater than epsilon px of a, right? But this probability can be easily bounded using after all, what is mu xn of a? It is this quantity sum I going from 1 through n of the indicator of xi divided by n px a is greater than epsilon px of a, and simply using the Chernoff bound you get that this is less than or equal to sum over all a in x 2 times e to the minus epsilon square the mean, which is px of a divided by 3. Right, so, and this you can get this bound easily from, say, Wikipedia. Right, so this is one bound which is not very tight, but it's reasonably good, and therefore this is, and this, so this is a very tight bound, and therefore this is essentially, since script x is independent of n, sorry, this is n times epsilon square px of a divided by 3. This is essentially 2 to the minus, so you can write this as less than or equal to 2 to the minus n epsilon square alpha of px for some suitable function alpha, right? Okay, so this property tells you that this is a high probability set, and indeed that is what we in the context of our compression scheme, where we wanted to choose an S, right? So we want to choose an S which is a high probability set, right? Because the probability of error, if we choose a high probability set, then the probability that xn is not in S will tend to 0 as n tends to infinity, which is what we want. Now for this set, we want to get a bound on the rate. We want to show that the rate is small, right? So what is the rate if achieved using the strongly typical set? Okay, so to find the rate, I'll prove an intermediate result, which turns out to be very powerful even outside the problem that we are trying to currently solve, right? So given any positive valued function gamma from the alphabet to r plus, and given any typical sequence xn, so any sequence in the typical set is called a typical sequence. So for any typical sequence and any positive function gamma, the sum I going from 1 through n of gamma of xi is always close to the expectation, and the way to see it is the following. So this is sum I going from 1 through n gamma of xi, which I'm going to write in the following way: a in x of indicator a of xi times gamma of a, right? So clearly this quantity, so indicator a equal to xi is 1 only if xi is equal to a, and therefore this quantity is equal to gamma of xi. You should convince yourself of this quantity within the in this region, right? So if I interchange the order of summation a in x 1 through n indicator a I times gamma of a, then what do I know for any typical sequence? What do I know about the indicator a of xi? This is always within x. So this is always within 1 plus or minus epsilon of px times n. So there should actually be an n over here. So this summation, sum over I from 1 through n of indicator a of xi is always less than or equal to 1 plus epsilon times px of a times n, and 1 minus epsilon times px of a times n times gamma of a. Okay, so this holds for all typical sequences xn. So if I take this outside, right, so it is in the range 1 plus or minus epsilon of n a in x of px of a times gamma of a, but this quantity is simply the expectation of gamma, expected value of gamma. So this is in the range n times 1 plus or minus epsilon of expected value of x, right? Okay. So what we will need in particular to get bounds on the size of x, we'll need the property that so a very special case is when you take gamma of x to be 1 over n log p of x. Okay. Let us take gamma of x to be equal to, let me choose gamma of x to be 1 over n log 1 over p of x. What is the expected value of gamma equal to? Equal to 1 over n gamma of x to be this. Yeah, so choose gamma of x to be log 1 over p of x. So the expected value of gamma of x is the expected value of log 1 over p of x, which is the entropy of x, right? So in particular, what the previous result says is that for any typical sequence, E epsilon r n of px, the sum I going from 1 through n of 1 over n log 1 over px of a, this is less than or equal to h of x times 1 plus epsilon and h of x times 1 minus epsilon, right? Or another way to put this is that Pxn of xn. So let me rewrite this. Right? So what is this equal to? So this is also equal to 1 over n times the log of 1 over product I going from 1 through n of Px of xi. But that is essentially, since if xn is a memoryless sequence, then this is 1 over n log 1 over Pxn of n, right? So for any typical sequence, any sequence in the strongly typical set, 1 over n log 1 over Pxn of xn is between h of x times 1 plus epsilon and h of x times 1 minus epsilon, right? And if you go back to the definition of a strongly typical set, this is weakly typical set, and this is essentially the same, except that this is h of x plus epsilon, whereas this is h of x into 1 plus epsilon. So if you had slightly defined weakly typical set as a set of all sequences whose probability is between 2 to the minus n h of x into 1 plus epsilon and 2 to the minus n times h of x times 1 minus epsilon, then we would have got the same thing, right? So every sequence in the strongly typical set also satisfies this property in some sense. But the reason why I brought up this weakly typical sets, although we are not going to use it now, is that weakly typical sets are what are used by the textbook, the Core and Thomas textbook, to prove the source coding theorem. Whereas in this lecture, I'll be proving it using the strongly typical sets. Right? So the strongly typical set has very nice properties and has more powerful properties than the weakly typical set, and are used for various other problems as well. So it's a good thing to be exposed to. Okay, so now we have this nice property, and we've seen the connection between strongly typical and weakly typical sets. We should now get a bound on the size of the strongly typical set. Okay, so this will sort of complete one major part of the proof, and the trick to proving a result of the form over here is to observe that the probability of that any sequence xn is in the strongly typical set. So this is a strongly typical set, but I won't use str and n everywhere, just for ease of notation. So the probability that xn is in the strongly typical set is always less than or equal to 1, because after all it's a probability, right? But we can also get a lower bound. So note that from property 1, right? So from property 1, the probability that xn is not in the strongly typical set is less than or equal to 2 to the minus n alpha epsilon square, right? So this probability that xn is in the strongly typical set is greater than or equal to 1 minus 2 to the minus n epsilon square alpha, right? Okay, so so now what I'm basically going to do is rewrite this in a certain fashion. So this is the set of all xn in the epsilon in the typical set of Pxn of xn. So let's try to prove this right hand side over here. Now this probability is always going to be greater than or equal to, so for any sequence in the strongly typical set, Pxn of xn is always greater than or equal to 2 to the minus n times h of x times 1 minus epsilon. We just got it from here, right? So this basically tells you that Pxn of xn is between 2 to the minus n, 2 to the plus n minus n x times 1 minus epsilon and 2 to the minus n times h of x times 1 plus epsilon, right? So this, okay, so Pxn of xn is always greater than or equal to 2 to the minus n times h of x times 1 plus epsilon, right? So using that fact over here, we get that this is, so Pxn of xn is greater than or equal to 2 to the minus n h of x times 1 plus epsilon, right? And this is equal to the sum, so this is less than or equal to 1. So I can take the 2 to the minus n h of x times 1 minus epsilon outside the summation and take it to the right. Epsilon of 1 is less than or equal to 2 to the n times h of x times 1 plus epsilon, right? But what is the left hand side equal to? This is simply the size of t epsilon, right? So size of t epsilon is less than or equal to n h of x times 1 plus epsilon. And using a very similar technique on this inequality, we get that this is also greater than or equal to 1 minus 2 to the minus n epsilon square alpha times 2 to the n h of x times 1 minus epsilon, because we'll have to use this inequality in the second part, right? Okay, so this gives us very tight bounds, and in particular it tells us that if we choose the set S to be equal to t epsilon strong, then the rate, which is 1 over n log size of t epsilon, this, as n tends to infinity, you plug all of this in, then this tends to h of x. It's h of x, so it's between h of x minus epsilon and h of x, h of x into 1 minus epsilon and h of x into 1 plus epsilon, right? So it's in this range between h of x into 1 minus epsilon and h of x into 1 plus epsilon, but epsilon is arbitrary, so you can choose it as small as you want. So the achievable rate is close to the entropy of the source, and the probability of error is of course vanishing in n, because we saw that the typical set is a strongly typical set, so we saw is a high probability set, right? Okay, so now we've demonstrated the existence of a set which is a high probability set, and 1 over n of log of the size is close to the entropy. So therefore what we've essentially shown is that there exists a compression scheme for which the probability of error is vanishing in n, and at the same time the achievable rate is h of x, the entropy, right? So this is typically called an achievability proof, and sort of one part of the proof of the source coding theorem. So we've shown that there exists a compression algorithm which achieves a rate close to the entropy. The next question is this the best that we can do? And it turns out that indeed this is. And the way to prove it is going to be pretty similar. So you take any set S, which is a high probability set, right? So this S describes another fixed length compression scheme, and you look at the probability that xn is not in T epsilon intersection S. So look at the set T epsilon intersection S. So this is Xn belongs to some, right? Right. So this effectively, so the probability that Xn is not in T epsilon intersection S is the same as the probability that X is in T epsilon intersection S the whole complement. But T epsilon intersection S the whole complement is T epsilon complement union S complement. And using the union bound, this is less than or equal to the probability that Xn is in T epsilon complement plus the probability that Xn is in S complement. Right? Great. So this is 1 minus the probability that Xn is in T epsilon, right? Or another way to put this is that this is the probability that Xn is not in T epsilon plus the probability that Xn is not in S, right? But what are these quantities? So this is equal to the probability of error of the compression scheme using the strongly typical set plus the probability of error of the fixed length compression scheme described by S, right? And for a good, so if you have any S which is good, then this probability of error PES should also tend to 0 as n tends to infinity. Okay, so this is one thing. Now what is the size of T epsilon intersection S? T epsilon intersection S has size less than or equal to that of S, and assuming that this total probability of error is less than or equal to epsilon as n tends to infinity, so that's what I denote as less than or equal to subscript n of epsilon. So this means that limit as n tends to infinity of LHS is less than or equal to epsilon, right? So the probability that Xn is in T intersection S is greater than or equal to 1 over epsilon, is greater than or equal to 1 minus epsilon for all sufficiently large n. But again, manipulating this, so if we write the probability of Xn is in T epsilon intersection S as the sum over all possible Xn in T epsilon intersection S of 2 to the minus n times h of x minus epsilon, or 2 to the epsilon. If you choose the strongly typical set, then this is 2 to the minus n h of x into 1 minus epsilon, right? And once again, taking this quantity outside the summation and taking it to the right, we get that the size of T epsilon intersection S is greater than or equal to, for all sufficiently large n, 1 minus epsilon times 2 to the n times h of x times 1 minus epsilon, or but this is less than or equal to the size of S, right? So the rate 1 over n log size of S is greater than or equal to, for all sufficiently large n, h of x times 1 minus epsilon plus the little of 1, so some quantity which tends to 0 as n tends to infinity. So note that S describes some fixed length compression scheme. We didn't assume anything about S except that it had a vanishingly small probability of error, right? So irrespective of what fixed length compression scheme you choose, as long as the compression scheme has a probability of error which is vanishing in n, the rate of the compression scheme is lower bounded by entropy times 1 minus epsilon. So for any fixed length compression scheme with a vanishing probability of error, the rate as n tends to infinity is always greater than or equal to h of x. So combining the results that the two results that we had, where we designed a fixed length compression scheme using typical sets, and we gave a lower bound on any fixed length compression scheme with a vanishing probability of error, we have the following theorem, also called the source coding theorem, which was originally due to Shannon. And it says that the minimum asymptotic rate of any fixed length compression scheme for a memoryless source, that is for a source which has IID components, the minimum asymptotic rate is equal to the entropy of the source. Right? So this gives an operational meaning to the entropy of a random variable. Right? Okay. So with this, we'll end this lecture. This lecture must have been a bit hard because a lot of new concepts were introduced. The best way to understand this is if you work out the proofs on your own, and you can also look up the textbook by Cover and Thomas. Most of this is covered in I think chapter 3 on the asymptotic equipartition property. Cover and Thomas chapter on asymptotic equipartition property. Right. The only difference between what was covered in this particular video and what is in Cover and Thomas is that Cover and Thomas uses weakly typical sequences rather than strongly typical sequences that I've used in this particular lecture.